create an accurate model to predict the power output of a combined cycle power plant based on certain ambient conditions. It is first important to understand how a typical power plant works. First, there is a gas turbine which compresses ambient air and pushes out hot exhaust gases. These hot exhaust gases are used to operate a boiler which creates steam and operates a steam turbine. This combination of a gas turbine and a steam turbine increases the efficiency of the system, since it helps recover energy from exhaust gases that otherwise would have been wasted. So why do we need a predictive model in the first place? Since currently there are little to no predictions about the power output based on ambient factors, it can get challenging and expensive to operate such a plant. These extra expenses can come in the form of extra fuel purchases or machine downtime or building permanent extra capacity, or by mistake not planning properly and building lesser capacity. With a predictive model that can operate in real time based on changing environmental conditions, these issues can be addressed better and the power plant can be run continuously and in a more cost-effective manner. To create any model, first we need to understand the data we have. For this power plant, we have about 9,600 hours of data. Each observation measures the ambient temperature, the ambient pressure, exhaust vacuum, and the relative humidity. Overall, each of these factors affects the output power and or the efficiency, and therefore can be key determinants for the power output. Before diving into creating a model, it is important to understand the general trends and patterns in the data. This will help us also better understand what kind of model we need to create. As can be seen from the individual factors plotted against the power output, there is a linear trend between temperature and the vacuum with regards to the power output. The other two factors, ambient pressure and relative humidity, don't particularly show a strong linear relationship, but that could also be because these factors may be correlated to other factors. Based on these preliminary observations and the type of data available, a linear regression model seems to be the most appropriate. It is a relatively simpler model and can be deployed easily at the site. The cost of compute will remain low, yet the model itself could be quite robust. We will create 3 models wherein we shall start with a model comprising of all input factors and subsequently create another model with one lesser factor and so forth. The factor to be eliminated at each step will be based on the impact of the factor on the output. We will split our dataset into a training set as well as a test set with a typical 80-20 split. Our output accuracy is important, while at the same time we also need to be careful about the factors we are choosing so as to predict the variance of the power output better. We will measure model performance by comparing the R-squared value, the RMSE and the MAE. Comparing the MAE and RMSE will help us with accuracy and be cognizant of any outliers that would affect the final performance. Comparing the results of the 3 models, it can be observed that model 3 had the overall best performance with an improvement in test performance from training performance. Models 1 and 2 had the opposite results, which could indicate overfitting. All 3 models had a very high R-squared value, indicating good prediction of variation of the output power. As can be seen, the RMSE and the MAE reduce from the training to the test performance data. This indicates that the model performs better with new data and therefore is more adaptable. This is not the case, as can be seen for the other 2 models. Therefore, in conclusion, model 3, where we consider temperature and exhaust vacuum only as the input factors, performed the best. The model performed well with new data and therefore seems very adaptable, and the absolute error percentage is also quite low, close to 1%. In the future, to get more accurate predictions, we could explore models with additional factors like seasonality and the time of the year to understand how output changes with time of the year. We could potentially also look at more complex models if the level of accuracy desired is much more.